Great. So, welcome everyone to this virtual meetup, 22nd PyData Cambridge meetup. So yeah, we've been going on for some time, and we're doing virtual meetups now in these last months, of course, because it's been because of the circumstances with the pandemic. So we have a great agenda today. So we've got an intro. We have this intro slides, and we have speakers from one of our sponsors, Fetch AI. So it's an introduction to the Decentralized Delivery Network, DDN, by Josh and Aris. And we also have a speaker from Decoded, Why Battery Powered IoT Data Acquisition is Hard, which both of them should be really exciting. So who we are. So we are PyData Cambridge, which is our local Cambridge, UK meetup. We started in November 2018, and we do monthly meetups, and we do this every last Wednesday of the month. This is organized by me, Federico, Joris, Leandro, and Ole. So in this call, I believe only Ole and me are at this time, but we're always here to help you out with anything dealing with the meetup. And of course, we are, our parent kind of company charity is NumFOCUS. And essentially NumFOCUS is all about, open code to create better science. So it supports a lot of the libraries that you might be doing in data science, in doing data stuff in Python and other languages. And PyData itself is an educational program of NumFOCUS. So they support us, for example, us being able to have this webinar on Zoom, to be able to have the infrastructure on Meetup. That's how, in a way, they sponsor this meetup, but we are an educational program. So as I said before, there's many libraries that NumFOCUS supports. Some of them you can see on the left. I personally use NumPy, Matplotlib, Jupyter, but there's many others that many of you can use. So yeah, I would personally ask you if you would consider donating to NumFOCUS. With the pandemic, normally NumFOCUS finances itself with a lot of conferences, and in this case, not a lot of them are happening. So if you are able to, please do donate to NumFOCUS. We do have a code of conduct, so it's essentially, you can read the code of conduct, and this is the PyData code of conduct. But in essence, it's basically says that you have to behave professionally. For any code of conduct violations or anything you would like to tell us, please contact us in the meetup, or you can also contact Leonie Muerk, which is someone who is independent from the organizers, who is a member of a committee in NumFOCUS. Okay, so before we go to on sponsors, I wanted to do a bit of try out a bit of an interactive presentation. So I would like to launch a poll, and please vote and let me know if you're a first-time attendee and what is your background. I'll keep the poll on for 1 minute and see if people can vote and get a bit of a feeling. I have a feeling that our virtual meetups makeup of people who are assisting is a bit different from our in-person meetup. Cool, so I leave it a bit more, and maybe you can get a bit more answers. Wait for a bit. Okay, almost done. I think the panelists can also reply if they want to. So I'm gonna end the poll in 1, 2, 3, 2, 1. Cool. So if you're interested, here's the results. So it seems like a lot of people are first-time attendees. So welcome everyone who's a first-time attendee. It seems like most of you are either data scientists or developers, which is actually quite a normal thing in the PyData network. It seems like conferences get more senior leadership too, but I would assume, yeah, maybe for a meetup, senior leadership have too little time, but they only go for conferences. Well, this is really interesting. I'll keep it. I'm going to take a bit of a picture of it and see. Thank you. And well, I want to thank our sponsors, which in the past would be paying for pizza. In the case of Raspberry Pi, hosting us in their headquarters. But in this case, well, it's difficult to do pizza, obviously. But this is still the companies that are helping us keep this meetup running. And sometimes pay for some expenses for speakers when they travel. Obviously, there's no traveling right now. So we do have a job board for different sponsors. So I'm a data scientist at ARM. So if you want to talk about any of these positions, you can speak to me. And essentially, the first job in this job board is from our team. So my team, so it's a data scientist position, but there's other positions like machine learning, system analysis engineer, staff performance analysis engineer, principal data engineer. So please let me know if you want to speak about any of these. Fetch AI, we have 2 speakers from Fetch AI, so I think they would be happy to speak to you if you want to know anything more. So yeah, they have a range of positions like DevOps engineer, software engineer, machine learning scientists and engineers, web developer, etc. But if you want to know more, obviously this talk soon will tell you more about what they do. There's also updates in the PyData network. There's the PyData Global, which is happening in the 11th of November to the 15th. So since there's no PyData conferences, there's going to be this PyData Global. The call for proposals is already closed, but please do consider attending this kind of online conference. So I've said a lot, please contact us. One of the reasons is that we are always looking for speakers. If you know someone who would like to speak in our meetup, please let us know. If you'd like to speak yourself, we are always happy to arrange this. And we're also looking for sponsors. It's running this meetup right now does not have a lot of costs, but we hope to go back to physical meetups soon. And with that comes a lot of cost if we want to offer people pizza and drinks, and if we want to pay for speakers to travel from other parts of the UK. Please follow us on Twitter on PyData Cambridge at PyData Cambridge, and please email us for anything about code of conduct. If you want to contact me about any of the jobs or any other contact for you, any other reason you want to contact anyone from our organizing committee, please write to us in the email PyData Cambridge. And that's it for me. So let's get this started. So I'm going to stop sharing. And Josh or Aris, I don't know who's starting, but you can start.
Yeah, so Aris. Hey guys, I'll introduce us. I'm Josh, application lead at Fetch AI, and I'm joined by Aris, one of our senior software engineers. We're part of the applications team, so we're building multi-agent systems on top of the Fetch AI infrastructure that we're building. So Fetch AI is building a blockchain and a little bit more. So if I take what we're building from our webpage, and it's Fetch AI is building an open access, tokenized, decentralized machine learning network to enable smart infrastructure built around a decentralized digital economy. Now, what this means is Fetch AI is building a blockchain ledger, which enables machine learning at the nodes and in the smart contracts. And on top of that, we're building a smart infrastructure, which is an agent-based multi-agent system that enables us to bring some form of digital economy to individual entities that are represented by agents. And the agents are what me and Aris will be talking about this afternoon. Over to you, Aris.
So yeah, I'm going to demonstrate the trains demo. And yeah, my name is Aristotelis. I'm software engineering at Fetch AI, as Josh pre-said. And yeah, we're demonstrating the decentralized train demo. This is a link for the video that we uploaded some weeks ago. And yeah, so what is it about this project? This project collects a huge amount of data from different APIs, and we distribute this data in different agents. You can see this, this front end. This is a tool that we built in order to debug and visualize our trains. So how we get the data? We are working in the UK, and for that reason, we have access to these two APIs, the National Rail API and the Network Rail API. Both of these APIs are letting us get updates for train creations, cancellations, and movements, and also for the boards for the stations. And this enables us to accurately position every single train in the UK on a real-time basis. You can see we can get details like the operator name or the platform or the time of departure in this case. And let's talk about the whole architecture of the system. The whole project is built around the agent framework that we built in the Fetch AI. So we have, I'm going to explain a little bit more about the system in later slide, but for now you can see that we have 3 entities that communicate with each other, and then we have a standalone peer node and the SOEF. Yeah, I missed something. Anyway, so the whole concept is that we are going to have all the agents running on the SOEF, so we are able to discover them, negotiate with them, and finally transact. So how this works? Let me find that. Yeah, nope, I'm missing a slide. Anyway, the agent manager actually communicates with the pool manager to get a fresh agent, a pre-built agent, so we don't lose time to create them on the fly. Then the agent manager runs the agent, and then via the multiplexer sends a message to that agent to update their data. The key here actually is we are using the peer-to-peer agent. This is a standalone AA framework agent that enable us to connect all the agents and the multiplexer of the agent manager as clients to that node, and therefore we can actually exchange messages with this agent. So the base concept, as I said before, is to find the agents, to be able to communicate with these agents, negotiate with these agents, and finally transact. For that reason, we are actually create a client agent. These client agents enable us to search the OEF node for possible sellers. The sellers in this situation are the trains and the stations, and they're selling data about the position of the train, if the train is late or on time, and for the stations, they sell actually the boards. We are searching in a radius of 50 kilometers around the client, and then we transact with this with the agents that we can find. So at this point, I think I can do a live presentation if I find the correct. Yeah, that's it. So we're running the peer node here, and then we're going to run the agent manager. This is going to create all the agents we want to publish in the network and connect to the peer node. Give it a minute. So we're creating the pools, and then in a minute, you will see that we are receiving messages and we are creating agents. So these are the messages that we are receiving and sending to the agents. And we can actually verify that we are having agents by going to the SOEF site here and check that the number here is getting up. So since we have our agents running, and getting details, we are going to run our client agent. This client agent is going to search in a specific location 30 or 50 kilometers around it and buy all the data from the stations and the trains that we can find. Sometimes takes 1 or 2 minutes to find a possible agent. So yeah, you will give me a minute there. The other part that I can show you until we get an agent is once we have a transaction, we will be able to see the transaction in the agent one. This is the Cosmos ledger that we have in Fetch AI. So we found 2 agents, and what happened here? We found 2 agents, and then we are sending an SFP. We are accepting the proposal, and we are paying for this data. And once we have the transaction completed, and the train agent or the station agent verifies that we got the tokens, we are sharing our data. In this case, we have a train, agent type train, with all the details that we need, and similar here. And we keep looping here until we stop it. And if we refresh this page, you can see that 22 seconds ago, we did a transaction on Cosmos Ledger. So actually, this is the trains project. Thank you very much. And I think Josh can take over from here.
Yeah, thanks, Aris.
No worries.
I'm trying my best to figure this out. Let me share my screen. Right, there we go. So I'm going to just rush us over to here. So can you hear me okay and see? I'm assuming that's fine.
Yeah, it looks good.
Excellent. So yeah, I'd like to introduce the Decentralized Delivery Network. This is quite a large project comprising of multiple parts. So this presentation's mainly on the connectivity of agents and the protocol defined to allow multiple agents to communicate using one set of standards. So before I go into the overall details, I'm just going to take you to like a web view of what's happening. So this is running a simulation, and you can see these grey dots are effectively drivers going to a passenger to pick them up. These passengers and drivers have found each other over the peer-to-peer network, and they're registered on the simple OEF. I'm going to get ahead of myself here and introduce these a bit too early, but the OEF effectively is where agents would register. So if you can think of that as a search engine for agents, and the peer-to-peer network is how agents communicate with each other. So these taxis and drivers and passengers are kind of finding each other and doing a journey, and I'll kind of flip back to this as I explain things as we go through the project. So the Decentralized Delivery Network. This is designed to give an individual in the gig economy autonomy. So the idea is that if you're a driver for any of the ride sharing apps, if you're a delivery person for any of the food delivery services, you can effectively stop working for those services, or at least reformat how they work, and have a lot more control over how you work. And you can, in this way, with an agent representing you, you can effectively negotiate with restaurants, with people, with passengers about how much it would take and how much it would cost for your services and how long it would take for you to get to them. The agents are built using the agent framework, something that Aris mentioned earlier and we mentioned at the beginning of the presentation. The agent framework is a Python library that you can download and build on top of to build agents to form multi-agent systems that can connect with Fetch AI agents, but any agents that you're building at that time. The project uses a specialized negotiation protocol, which is the DDN. Using this enables drivers to deliver people, packages, and food. What I've shown you is an MVP. It's controlled by a simulation. So effectively, there is a simulation class in the background that's controlling the agent's position and affecting overall state. Now that could be whether or not a passenger thinks a fare is too much money. It could be whether or not a driver decides to take a 10-minute break, or just general how much a passenger or driver would like to spend or be where at they would like to be. So continuing. So the core ideas, I think this is just good to kind of reinforce, because I'm not entirely sure everyone knows who Fetch AI are. So the agent framework, as I've said, is a Python package, and we use it to build multi-agent systems. All of the applications that we build in Fetch AI will use the agent framework when building agents. We're using blockchains, our own, Ethereum and others. We use smart contracts, and if you're not aware of what smart contracts are, in the highest level sense, I like to think these as predetermined, immutable rules somewhere online that we call and get a response. We can update them sometimes too. The system, the DDN, is a system that gives gains for independent people. It effectively connects entities, and these entities can be cars, can be people, can be products, and represents them as agents. These agents can be very intelligent. They can just be quite simply returning the date and time. The agents are fully customizable, and they run with very little overhead. They can run on your phone or watch, providing that they meet protocols to connect with other agents. And finally, an agent really could take up a whole data center if it was doing any form of prediction modeling for weather. So from there, I introduced the architecture, and I realized this is going to be quite small on your screen, so I've got it in another image to the side. This side, here we go. So the DDN is kind of composed of two individual parts. We've got the centralized layer, and we've got the decentralized layer. So the centralized layer is not something that I want to spend too much time with, but to get lots of decentralized entities information onto a web page, we have to have a message passing server, basically, and a way to get to a web page. So we're using Kafka because it's very good at handling vast amounts of messages. We then kind of pass that and feed that out to web pages that connect to it. On the decentralized side, which is basically how the agents, where the agents live, we've got the agents, we've got their communications to the peer and the SOEF, and finally we've got their connections to the blockchains, where we're mentioning Fetch AI and Ethereum and other. So to break down what these parts are individually, the peer-to-peer layer, where the agents talk to each other. The OEF layer here, the simple OEF, handles registration and search, and then finally, bottom left, the blockchains are recording transactions and could be where smart contracts have been deployed to. So the agent itself is comprised of 4 core parts. There could be more depending on your agents, but for us, we have a connections, contracts, protocol, and skills class. So the connection class of the agent, it manages the connections to the peer-to-peer layer, connections to Kafka to update its state to the front end, and finally the connection to the simple OEF. The connection only controls the connection, so it doesn't have any logic that would control data coming through. It will just effectively take a message from the skill layer and send a message to the skill layer. It's very, very, very singular in what it does. Additionally, we've got the contracts class, which handles the interfaces and contracts to a blockchain. This is where your agent would say, you can download these contracts from our repos and deploy them within the agent as such. And the agent will effectively have a reference to these contracts and then deploy them for whatever use they may have. So in our case, we use an escrow contract, which I'll explain a little bit more in the next slide. And that kind of manages the payment and negotiate payments between a driver and a passenger. Then we've got the protocol, and this effectively defines how drivers, passengers, food, and, well, yeah, drivers, passengers, food, parcels will communicate with one another. So Kafka is defined so that we always send the same message structure to Kafka. Location is defined because that's the simulation basically needs to always be sending the right data across the project. And then taxi is now known as the DDN, and the DDN defines how a passenger would talk to the driver, and the driver would talk to the passenger. Finally, the agent has a skill class. This manages core logic of the agent. So we've got the identity, which you would think of as, in our case, we've got a proof of identity, but in a driver's sense, they might have a carriage license, perhaps scans of any kind of identification, a unique public address for each blockchain, and yeah, that basically. Additionally, it will have skill like logic that would say, if I was a driver, but I drive a very fancy Mercedes, so I only want to take jobs that are over £100 or whatever digital currency we're using at the time, that kind of logic would be in there, and that would filter out the messages that come through the connection to align with that strategy. Additionally, we have a database. This database is pretty essential for localized history, and eventually this ties into our machine learning strategy within Fetch AI. So this data can be uniquely used in a privacy preserving manner to update pricing across multiple drivers, for example. And then finally, we have a class which is simulation, which really isn't very important for this agent, but the simulation manages the taxi and the state of the system, as I've already described. Continuing, as I've mentioned before here, that our protocol for the DDN is how the system works. The protocol is best defined in this one-way system, and if I go over to here, I can probably talk about this and iterate through. But when a passenger connects, it sends a call for proposal to the network, and this is propagated through the network with a peer-to-peer layer. If you're a driver that's looking for this message, you will see this proposal come through, and in green here, you will action no request. This request will probably ask for more information, but it's not always essential. Then the passenger will respond, and if I can just zoom in here a little bit. This response will say to the driver, do I or do I not want this, this journey? The driver here can decline, and in these first 4 kind of actions, this is where the core negotiation will take place, and the request and response can iterate almost indefinitely until one of the agents decides within its skill that it will only negotiate to say 10 layers, whether or not the journey will continue. So if the journey does continue, after the response, the taxi driver will send a proposal to the passenger. So in this example, we assume it accepts. But if it doesn't accept, this proposal could then be followed up by a decline, and the decline has a valid response as a call for proposal, and it iterates back on itself. It's actually more of a graph of communication than it is this one-way system that I'm showing. So if the proposal is accepted at this point, the passenger will send the driver an accept, and the driver in return will send a contract address where the passenger is to send funds for the journey. So when the passenger sends funds, the driver will check for a deposit, and then the driver will start to send updates once the funds have been verified. So what is happening there is a contract deployed on the blockchain that the driver owns. Additionally, the driver is not the only owner. There is a dispute resolution owner, and this contract will state the agreed amount between the passenger and driver. And at the end of the journey, if the journey was fine, the passenger will effectively, well, the passenger can release the funds, or the passenger can time out, and like after so many block confirmations, the funds would be released automatically. If for any reason there is a problem with the journey, and the passenger's just, perhaps the driver hasn't turned up, or the passenger says stop midway through the journey, and the passenger doesn't want to release funds and makes that clear, the dispute resolution service can come in, which is another agent, and can calculate how far through the journey the journey was. So to do that, there is a proof of location concept in the project where at each point, say every 20 seconds, the driver and passenger will do a handshake at a certain location and agree that they are there. And this is all happening in after the pickup, sorry, but this relates to the contract. This will then be signed to the contract, and then you'll have a small history within the contract that says I got so far through the journey, and then based on the rate that's been defined for the journey, the dispute resolution agent can effectively divvy up funds at that point. So the contract's quite specialized for the DDN, but we're constantly changing this and running new simulations on how these contracts can work. So to go back, the funds have been deposited to the contract, and now the driver is updating the passenger to say, I am on my way to collect you, or I'll be there in 2 hours, or they might not say anything because the journey's the next day. When it comes close to picking them up, they'll say, you know, I'm on my way, and then eventually they'll say, I'm outside your house, I'm here to pick you up, or outside wherever. At that point, they'll handshake to say they're in the car, and that goes back to the logic I was talking about, where the driver and passenger agree they are in the car. So now they're agreeing that they're moving, and this will be happening. Well, when this driver here picks up the passenger, they'll be sending this update to every to the contract to say they are where they agree they are. So going back, once the handshake's been made, when they get to their drop-off location, the driver and passenger agree that this is the drop-off point. They'll handshake again, and then the journey will be complete. At this point, the complete will end the loop for the passenger, but the driver will have been continuously in this call for proposal loop, building up the next journey, and the next journey, best fitting for their schedule. And this could change quite often, but they're going to be choosing their best fit based on where they are. So it will almost always be the closest journey, so the gap isn't as far, or it could be the best price. But we're constantly changing this, so we're simulating to work out what could be the best financial interest for drivers in this situation. With the journey complete, we will, if the passenger doesn't release funds, as I mentioned earlier, there's a timeout in the contract that would release the funds to the driver. Okay, so just go back to the presentation. Nope. Yeah. So that actually was as far as I wanted to cover with the DDN. I'll just show you a snippet of code because we haven't planned to show too much, but this is quite interesting. We have the protocol specification here for what I've been talking about, which is the DDN protocol. And we have in the agent framework a command that can generate all of the code that runs for the protocol from a simple definition. And this kind of shows the idea where I described that we're communicating across a bunch of nodes and vertices, edges. So the idea is that in the beginning, a passenger will send a call for proposal, and that can only be met with a request for more information, a decline, or an update. A request can only be met with a response or an update. And then as we go through it, a journey complete, for example, can only be responded to by a release or an update. And that is effectively how we're building the project and as the protocol. And as we develop this does have a lot of extra bits in here that we haven't shown, like at collection point, at drop-off point. This is tying into our parcel collection and delivery, which we do have working, but the develop branch is a dangerous branch at the moment. So I can't really show that. But the idea is that a driver, if economically viable and they don't have many journeys up to a point, they can choose to pick up parcels on behalf of parcel delivery companies and then schedule in to drop that off at a depot based on the journeys that are coming up in the future. With that, I'll just go back to the slides and show it's still going. So there'll be negotiations happening between the drivers that are in grey and passengers, and honestly, with a certain amount around and intervals of negotiation, it can take a little while for the drivers to find the passengers. Well, they've found them to agree with passengers. And yes, so presentation. With that kind of concludes everything I want to show with the DDN. As mentioned earlier, we have a range of opportunities at Fetch AI. We're looking for DevOps, software, machine learning, and web engineers. We're looking for a front-end developer, and if you're keen and in the room, where the applications team is definitely looking for a Python developer, you join me and Aris working on this. We're looking for a marketing and partnership manager, community manager, and social media and content executive. You're welcome to ask me questions or just email careers@Fetch AI. And that's everything from us.
Thanks, Joshua. if anyone has any questions, please put them in the Q&A and we will start answering them. To start it off, I have some questions that might be a bit silly, but let's see how it goes. So, so when I get into, taxi and you might say where I am through location services, but the moment I stepped into it, I tend to turn off my location, kind of saying I don't want to waste my battery.
Okay.
So you did mention that there's like a handshake saying, every 20 seconds of where we are. Would that be a problem in this? Will my behavior be a problem?
Your behavior would be a problem. So you wouldn't have to. So as a passenger, you could avoid any contract with a dispute resolution. You could just say, I'm going to pay these funds. I don't want to enter my contract. I'm just going to pay when they get here or pay when they drop me off. And some drivers will be okay with that. We're effectively in some ways over-engineering this and trying to create a what we describe as a fair system that benefits both the driver and the passenger. Yes. But yeah, there is realistically no hard rule that you need your location on.
Yeah, well, it does make me think if it's a problem in the current services right now, maybe I don't have proof of where I was. The other quick question I had was you did mention a little bit about how you solve those requests, and it's about a price or a journey. Is that in where is that logic? Is it part of the?
So that's part of your skill, and effectively there's a couple of parts to this, and it can be as complicated as you want it to be. But we have a YAML file where you can just you can imagine that this would be represented in a web page where you just fill in a few boxes and say what your preferences are in an app, and then they would be filtered through, and the agent would find and search by that. And yeah, that it's all happening within the skill. Once the message is passed to it from the connection layer, the decisions are made in the agent skill.
Cool. Yeah, those were my questions. Does anyone else have any questions? I would welcome to questions from any of the panelists if you want to.
Hi guys, sure. That was great presentation. Thanks, Josh and Aris. I guess when it comes to blockchain, a lot of the benefits are sort of around the sort of threat modeling. So decentralization means less points of weakness. You don't have to trust a single entity. That being said, and obviously you can answer this as freely as or not, but where would you see the sort of, not the weaknesses, but if you were a malicious actor, I suppose, how would you approach a decentralized system like this?
Okay, yeah, so everything I say, we're combating readily, but you as a driver could say, you could approve a job, and in the current system, you could say that my rate is a certain price, and then if you didn't turn up, or you did turn up and drive off, you could still get paid the journey to get to that position, if that makes sense. So you could just drive around, get into positions, and never let anyone in your car. That loophole won't exist in a few months' time, I'm sure, but right now that is there. We have introduced the concept of trust, and I haven't talked about that in this presentation, but it's not the goal of the OEF or the peer-to-peer layer to monitor transactions that go through at certain stages. So a secondary set of agents are monitoring all transactions that are going through the chain, and then looking for ones that have ended early. And you can do that by just checking the contract to see, because it will be publicly available, a lot of these variables, what contracts may have ended earlier than necessary. And you'll start to see a pattern. If a driver is ending journeys, very early on, they'll start to become a slightly untrusted member of the pool as such. But there's a lot of work to be done there on trust in a decentralized system, and some things we've not solved, like I've mentioned, but that's some of the more interesting parts of this, that's for sure. Thank you.
So there's 2 questions in the Q&A. I'll read out one. So might be a silly question, but is Fetch AI just developing the software, or are you yourself looking to be the company that taxis and drivers register to? Yeah, and apologies if it was covered in the first 5 minutes that they missed.
Good question. We're building the software, and we're building the framework to enable other companies to build the software to connect with this as well too. So I would say right now we're building the software to prove it can be done and prove that we're thinking about how this all ties together in a centralized manner. But from there, we're open to speaking with a lot of companies at this point. We're in talks with lots of projects, lots of interesting projects, and yeah, I think that's everything I'll say on that one.
Cool. So there's one more question. Do the drivers have the ability to compete for a transaction at all? Say if a second driver were a further distance from the passenger, but there was only one available job in the area. I think it's kind of related to my request question. Like, where does that logic exist, and can you as a driver play with it in a way?
Yes, there's a couple of things here. When the passenger does a request, two drivers will get that almost simultaneously, and if they're, say, 10 seconds late to the request, they'll still get it. It'll still be propagated through the network to the two drivers. Now, the passenger could say, I will wait 20 seconds for all responses, and then I will choose the best out of those 20 seconds. And if they do that, they will choose their best fit out of that pool. But if they're willing to wait longer, two agents, they will negotiate with each other, and one of these taxis will say, I will get to you sooner, or I will be cheaper, and then the passenger's preference will pick. Now, there's nothing stopping the passenger from still looking for this journey, even after they've agreed the journey with another driver and the driver comes to them. But if that happens, the passenger is going to lose, most likely, that base fee for that driver coming to them. Now, that idea is coming from the Uber model that we see now, and we've used. But if you were to look at other taxi companies that you can book a driver through, that logic doesn't necessarily exist. So this is going to come down to a lot of I want to say behavioral science and things that I'm not necessarily a specialist in, to kind of work with how people will behave to the idea that they have to follow through with a booking, for example, or cancelling. What the implications of that are.
Great, thanks. So that's all the questions. There's just one tiny one, is if you're gonna share your slides, but if you want to share your slides, we can definitely coordinate after the meetups for that. Well, then that's it. Thank you very much, Josh and Aris. And now we'll let Amadeus give his talk. We can have a tiny little break whilst Amadeus sets up.
Great, thanks everyone, and thanks again, Josh and Aris. Really interesting. The question which will segue into this talk is, when you're looking at data from, let's say, the train network, obviously those are physical devices hurtling around. Where does that data come from? It's great they have an API, but what lies behind that API? So obviously my answer is IoT, Internet of Things, which is what I'm going to cover today. Just a quick background before I start. I'm the head of product at Decoded. We're a tech education company. So we run enterprise programs around data literacy for leadership teams, and we run data skills programs for fledgling data analysts and data scientists. So very much education is the core of what we do. Before I worked at Decoded, I did my PhD in nanotechnology, and I actually shared an office with Fede. So thanks, Fede, for having me on. Our paths have diverged somewhat, but I'll bring it back to ARM at the end. So I'm going to share my screen, and this is very much not a work talk. This is the result of what is essentially a lockdown project. So it might be a tad less, not professional, hopefully, but still polite, but very much sort of a fun project. So the goal of this talk is to convince you all that data cleaning and modeling and engineering isn't the hardest part. Actually, getting the data in the first place is, especially when it comes to Internet of Things. The motivation for this project actually started about 2 years ago. I was living in the US. I was heading up the US team. I Decoded for 5 years. And my wife and I decided to move back to beautiful North Yorkshire. So we were living in the north of England in a very rural setting. And as any northerner knows, winter's coming. It's cold. So we need to do something about the heating. And actually, when you look at sort of mean temperature values across the country, obviously blue, cold, red, hot, Cambridge in the middle, it's pretty cold up north, although technically the north of England is actually about halfway up the UK, so it's not really the north, but I'll get in trouble if I say that to a proper northerner. So what did we inherit? Well, this is a slightly terrifying looking 1982 Kidd oil-fired boiler running off kerosene heating oil. It's a bit of a brute. You switch it on and it absolutely gobbles up oil. We've got mixed fuel stoves. I'm not going to be automating that. We've got classic electric heaters and combi boilers, as well as a few other bits and bobs. So I'm working in a very mixed fuel environment. And the motivation for this sort of project was primarily to reduce our environmental footprint. So how do we reduce carbon emissions, lessen our dependency on those, but also actually have hot living conditions. Don't want to live in a 10-degree house. Part of that also reducing costs, but also for me, technical stretch. So the aim of this sort of project, which is ongoing, was to build a highly efficient battery-powered thermostat-driven climate control system, or to retrofit antique, inefficient heating systems with the latest and greatest in IoT technology. So when I say IoT, Internet of Things, it's great because it could be pretty much anything. You can connect cars, trains, as we saw, phones, solar panel, power plants, whatever you want. It's a very broad concept around connecting inputs and outputs. So to start with, I needed a platform, and I actually registered for an account on Reddit, which I'd never registered for. And I said, hey, what does everyone use? And this great open source, Python-based Raspberry Pi compatible software project called Home Assistant. If you've used Home Assistant or use it, it'd be great to just drop a note in the chat. I'm always curious to see who's using it. But essentially, it's a pip install. You run it on a local server and you get this sort of interface. So it's pretty basic to start with. You get sort of things like weather out of the box based on location, but it's pretty much a blank slate. So this is the platform running on a little Nook, actually, in my case, but to give it a bit of extra juice. So as you can see in the photo, you can have inputs, you can track people, which I don't do, you can switch lights on and off, but I wanted to start with some outputs. So you can find all kinds of smart plugs. These are relatively cheap ones by Sonoff, and the idea is you plug them in, connect them to Wi-Fi using the app. But I don't want to use the app, I want to use Home Assistant. So if you go through all of the documentation, you can integrate it, but the integration involves you sharing your vendor login to Home Assistant, and basically what that means is your data goes up into the cloud somewhere, you've no idea where, and then the cloud is controlling your sort of 240 volt system. So I didn't feel very comfortable with the idea that I was putting my data out there in the cloud, and in theory someone could potentially manipulate that. So I opened up this device. So this is one of the smart plugs, and this thing in the middle here, this is called an ESP8266, and it's a chip which turns out is very common. It's been a really big chip in the sort of home automation scene. Somebody's actually done a die cut, so what they've done is they've literally just chopped off the top of the chip and taken a microscope to just investigate what's inside, and it actually has a bunch of different like neat things. It's got the sort of RX and TX components of the Wi-Fi network. It implements a full TCP/IP stack. So you can just run, you know, web, whatever you want directly on this. And all of these sort of little things are memory. So all of this stuff here is program memory. There's a separate flash chip as well, so you can actually store data. So it's an amazing sort of single chip solution that allows you to do some pretty cool stuff. So how do you get your software, not the manufacturer's software, onto this chip? Again, the community is fantastic. This is a project called Tasmota. So what they do is they've built an open source firmware. So hardware is the physical stuff, software is the code, firmware is in the middle. It's the code that you then install onto the hardware. And the reason it's firm is you can change it, but it's a bit harder. So it's not as easy as writing code. You need to flash, you need to transfer, which in and of itself isn't always that straightforward. So how does something like a Sonoff plug work with Tasmota? Well, it's great. They support a whole bunch of devices. They've got templates and all the inputs and outputs. The slight snag becomes, how do you then put your firmware onto it? So this is where you need to break out the soldering iron. Things get a little gnarly. You're working with these really tiny connections here. This is I can tell you these are absolutely tiny wires. And then once you've done that, you plug it into your computer and you flash it. So I'm not too unfazed by this. This is my home version. Obviously, I'm not plugging this into mains when I'm doing this, but you just have a USB adapter. It's called an FTDI. It's one of the common chips. You overwrite it, and there you have it. So then you have your own Tasmota plug. And the way it works is that the plug itself is sort of here. So that's the smart plug. And then the electric heater, in this case, sits on top of it. So essentially, it's a power proxy controlled by Wi-Fi. Really, it's a fancy relay. So let's have a look at, I'll just show you a live sort of version of what that looks like. Again, Tasmota works on the web, so your local network. So I don't have to worry, my threat model is people outside my house, not inside my house. So it's just running on the local area network, and you can toggle it on and off. I don't know, I can hear my heating turning on and off, and you can do a bunch of stuff in here. This, in turn, communicates via something called MQTT, which is a message broker. And again, super easy. You run it on a local server, and you define a topic, and it's sort of almost plug and play. So that's sort of what that looks like. Once you've done this for a simple plug, you can get a little bit more fancy and slightly non-regulation. This was, this used to be a mechanical controller for the big oil boiler. So I sort of ripped it off and I rewired it with a different type of Sonoff plug. I do need to cover this, and there are lots of electrical regulations that you should definitely get someone to check before you do this. Interestingly, for a combi boiler, it's sort of similar, but they actually contain two switches. One is the sort of main switch, the other is the pump to push the hot water around. So you can switch the boiler on, but then you switch on the pump to access that. So despite being a little nervous about doing this, it's actually worked out great. And of course, this is all going to be very safe and fireproof one day. So that's what the system looks like. And I think actually, if I just go back, just to show you how that integrates, you can then add a little card. It's really easy to do. You edit this and add a card. And now, slightly more easily, you can switch on and off. So these are the basic control mechanisms for doing this. So far, everything's pretty straightforward. The challenge is, of course, a lot of these dumb heating devices, whether it's an oil boiler or an AC unit, or in this case, an electric plug, they have very poor thermostatic control. So in my case, it's just min-max. What does that mean in degrees? No idea. There are sorts of standards on internal temperatures. I'm sure everyone's familiar with 20 or 21 degrees. I'd be interested to hear what people set their home thermostats to. But essentially, you need to somehow figure out how to turn this into an actual reliable heating device. So you can build your own sensor network for that, which is basically what I've done. This is something called a DHT22 temperature and humidity sensor. It's actually, despite the number of pins, I think it's a one-wire sensor. Anyway, you buy them, they're a couple of pounds on eBay, and you need to hook them up to your own device. Now, it turns out that there are lots of different ways you can run your own chips. So this is a development board for an ESP8266. So this thing here is, that's the module. It's a 12F, so it's the actual chip itself is about this big, and then next to it the RAM, and then there's some other bits and bobs. So if you can imagine, you get these kits where you get the module. The benefit of using these kits is you can do things like you can directly connect with USB. It has a voltage regulator, so you don't have to worry about that. But you should be able to see this is the antenna. You buy one of these. If anyone's used the Arduino, it's very similar. You can sort of control it like that. So that was great. You can plug all that in. What I'm going to quickly show you is the sort of logic behind how this works. So you power up the device, you read the sensors, you connect to the Wi-Fi network, you connect to the MQTT server, and you publish the data. So that, in a nutshell, is the simplest approach to what this looks like. All of this stuff's on GitHub, which I'll share the link later. But just to give you a sense of all you need, you just specify your Wi-Fi credentials, the address of your MQTT server, the topics, and then read the temperature data, connect to Wi-Fi, publish the temperature, and publish the humidity. So it's like 4 functional lines of code with some debugging stuff around it. So it's very straightforward to get this working. Once you've done that, you can then add them into your home assistant. So now what you're seeing is I've got the little badges. This is sort of real-time data. We'll see in a minute why it was 45 minutes ago. But you can also get history graphs, so you can sort of check the temperature. The reason it's stepped is because in the production code, I've set some sort of thresholds to make it more battery efficient. But if you really wanted to, you can get it to send the data every second or 10 seconds, and you get much smoother data. But anyway, that's what it looks like. So it's pretty neat. You've got your inputs, you've got your outputs. Controlling anything like this manually is obviously a pain. We want to automate that. So the brilliant thing about Home Assistant is software-defined thermostat control. So here, it's all configured with YAML, so not too dissimilar from some of the stuff we were looking at before. You define the heater. So this is the device which you're going to switch on and off, and then you define the sensor. So which specific sensor. So you can mix and match. You could put sensors in different places. You can actually combine sensor data. You can create software data. You can do whatever you want. It's a really neat system. You define your mins and max, but it's the target that really matters. So with a bit of soldering and a bit of sort of patience, what you get is a sort of Nest-like thermostat here. So this is, apparently it's 20 degrees, which is amazing. So I can't show you this turning on because my max, yeah, it's got a 0.2 degree differential. But basically, it's just like a Nest. You set the set point, you switch it on, and it will automatically switch itself on and off. You can get a sense of the history. So it's actually been switching itself on and off just a little bit over here. But basically, you've turned a really dumb electric heater into a temperature-controlled automated thermostat. You can then enable the thermostat during working hours. So step one in the voyage to efficiency completes. But, and this is the big but, this is a wired system. So it's connected via a plug, and anyone who's worked with temperature or any environmental data will know that the position is incredibly important. If you left this sensor on the floor, you get a much colder reading, hot air rises. So really what you want to do is, ideally you'd wear the sensor. It's get a bit crazy, but I popped my sensor underneath my laptop. You want to get the sensor as close as possible to where you want to experience that temperature. So I've got a cot downstairs with a 1-year-old in. It's not in the cot, it's near it, but I found that by moving that position, it made a big difference to the heat. So as a reminder, the aim of this sort of project was to build a battery-powered thermostat control system. And this is where data acquisition gets hard. So far, it's pretty straightforward. I hope you'll agree, 4 lines of code. Where things get tricky is when we try and run it off a battery. So previously, I think I showed that there's a sleep between cycles. But it turns out there are multiple kinds of sleep. The ESP8266 chip they've done a really good job of implementing different types of sleep, depending on what you need. Modem sleep, light sleep, or deep sleep. The thing that you want to focus on here is the current. So that's the background power consumption. So obviously you can see it really drops down to microamps, which is where you want to be, and deep sleep mode. But that means no Wi-Fi, no clock, and no CPU. There is a wake-up functionality for that. So let's implement deep sleep. And all you do in the flow is you change it to deep sleep, and then off you go. So sounds pretty straightforward. Great. Now all we need to do is get a battery, attach it to our updated code, and off to the races we are. Well, it's not that simple, because actually, when you look into it, these devices weren't really, in fact, Wi-Fi is not a battery-friendly thing. Turns out that there are various components on this friendly developer board which draw current no matter what you're doing, even in deep sleep. So there's an onboard voltage regulator, which converts it from whatever you give it to the correct voltage. There is the serial chip. So to get USB, you need a chip. Turns out that that's drawing, I don't know, probably about 200 microamps. So the sort of lengths that people go to retrofit, absolutely horrible. I'm not prepared to do that. So that was a sort of dead end. You can't just rely on hardware, to be battery friendly. Next step is I've got one of these ESP01F modules. I'm going to try and hold this up to the camera just to show you how small these things are. So hopefully it will focus eventually. Yeah, so you can sort of see you've got the Wi-Fi chip, you've got the actual ESP8266 chip, and then you've got the flash memory here. This entire thing is smaller than my thumb. So this is a very small chip. And I thought, great, there's nothing on here that can draw power. So we should be off to the races. Of course, challenge. Turns out that to get deep sleep, there is one wake up pin, which is how these things work. They go to sleep and they listen on one pin, and if that's triggered, then it will wake up. They actually left that off this design for some extremely strange reason. So what people have done is take extremely small wires. So you can kind of see on the left, this is how thin this wire has to be. and they've soldered it to the edge of this thing. Well, I invite anyone to try that on a chip that looks as small as the one I'm showing. I did try, it was terrible. I gave up. So what does that mean? We still don't have a chip that we can run off a battery. Well, you can actually buy the modules themselves. So I don't know if you remember, but on the dev chip, there is this small module. You can buy this, and there really is nothing on this. So that should be how we can attach a battery, and off we go. Great. Challenge number 7 at this point. What battery do you use? So batteries are fascinating. There are lots of different battery technologies. The ones that I'm sure people are familiar with are lithium ion, so phones. Zinc magnesium oxide is actually alkaline, so standard disposable batteries. The other one that's quite common is nickel cadmium, and then if you've got a car, lead acid. Each of these chemistries will have a different voltage range and discharge profile, and that matters because ultimately you've got a sort of target voltage. For most low power devices, it's 3.3 volts. So which one do you choose? How do you manage that? For sort of brevity, I went with lithium ion. And in fact, I took a leaf out of the old Nokia 3310 playbook, the classic snake phone. They're 3.3 volt battery lithium ion batteries. Sorry, they're 4.2 volt lithium ion batteries. Are very small. I've got one here. You can buy them on eBay for peanuts, well, a couple of pounds. My choice for using one of these is it's such a common phone that they're cheap. So tiny, effective, about 1,000 milliamps. But you need to lower that voltage and standardize the voltage, which you do through something called a voltage regulator. This is what's called a low dropout regulator, and this will drop the voltage from whatever it is within a certain range down to whatever you want it to be. And low quiescent just means it has a low background current. So the idea is to find one of these regulators which consumes as little current doing the job, all to save precious battery time. For anyone who's an electronic engineer on the webinar, they'll point out that LDAs are terrible for this because the difference in voltage, they dissipate as heat. So anyway, we'll get to that later. There are more effective controllers for doing this. So this is what it looks like. This is sort of the first prototype running off a battery. So this is the lithium-ion battery. That's giving you about 4.2 volts at full charge, and it will discharge down to about 3 point something. And the voltage regulator is actually pretty small. It's just a small chip. It's here, over here. So this then provides 3.3 volts. Here is the chip with a few small components, and then here is the DHT22 sensor. So that's sort of everything together. And it's a little bit messy, but it's a prototype. We'll look at how we're going to continue that later. But sort of Bob's your uncle, we're off to the races. However, we're not, because lithium-ion batteries have a really complicated charging profile. Unbeknownst to me, you can't just, unlike a lead acid battery or a nickel cadmium battery, you can't just trickle charge them, stick a solar cell on. They have different phases of charge. One is a constant current charge up until a certain current, and then there's a constant voltage charge, and it all has to be very carefully balanced. So that's probably why you read about warnings about badly charging lithium-ion batteries. They can go pop. So in order to do that, you can just find a chip that does this for you. This is just the first chip I found on Google. And again, you've got a standard voltage in, you've got your battery voltage out, and it will handle all of that. The fun thing here is you can differentiate between charging and not, and it's a binary output. If this is high, then this light will go on, nothing will happen here. It's low, the other way goes around. So it's clever use of sort of pins. Everything's very efficient at the sort of IoT level. So here's a picture of the one that I actually made. Just again, point out, these chips can be really small. So you have to have a very steady hand. A lot of these are surface mount chips. That's like an LED, you can kind of get a sense of the size. But anyway, it's all working. So a lot of effort to get a battery powered temperature sensor. You could separately just go straight with alkaline. So alkaline is about 1.5, so times 2, you get about 3. So actually with 2 AA batteries with no voltage regulator, you can directly power one of these chips. So a little bit fast and loose, but that's another way. This doesn't solve the environmental problem because this is non-sustainable. You have to throw these batteries away. Rechargeable AA batteries won't be alkaline. They'll have a different voltage threshold. You're back in the same problem. So this is probably about two months into the project. I get really excited. I load it up, drum roll. How long does this system last for? 9 miserable days. After 9 days, it drained the battery completely. So the the reality is, I'm sure many of you have thought, this particular flow is very inefficient. Every time you publish constantly, you're reading constantly, you might sleep, but what if there's no temperature change? You're still wasting energy. So going back to, going back to this, how would you store the state of the previous temperature and check for a change and before you connect to the Wi-Fi? Connecting to the Wi-Fi tends to be the most energy intensive process. Well, you need memory to do that. And as a reminder, in deep sleep, you've got no Wi-Fi, no system clock, no CPU clock, therefore no access to sort of memory. All you've got is a real-time clock. It turns out the real-time clock's role is to count. So you put it to sleep for 10 minutes, it needs to store that 10 minutes somewhere and needs to store the counter somewhere as well. So actually you can steal about 500 bytes of this real-time clock memory for your own purposes. So it's a bit hacky and it's quite low level, but it's possible. So what does that look like? First thing you do now when you power up, and I should just clarify, deep sleep means go to sleep, and when it wakes up, it just reboots. So that's the reboot. So on reboot, read the real-time clock memory. If it's valid, i.e. it was stored, then read the sensors, check if there's a difference, and only if there's a difference, connect to the Wi-Fi and publish. If it's not valid, just read the sensors, connect to Wi-Fi. So this sort of flow chart is what I ended up with. And just to give you a flavor of the complex, I mean, it's still very simple compared to the stuff we were saying before, but you do have to program in a lower level language. So this is essentially C. This shows you, this is the 512 bytes. You need to really be careful on the data types and the amount of memory they use. And also you need to understand things like floating point arithmetic and pointers. And I confess I didn't, and luckily I got a great friend I could call up on Zoom and he could help me out. So anyway, this is how you access the real-time clock. And remember, this is just to try and save a little bit of power so that this device lasts for a bit longer. So we've now got to a point where we are efficient. Does it work? Nope. Why not? Because in 2017, there is a closed issue whereby if you use this deep sleep switching off the radio, there is no way to switch the radio back on. No way to do that. So that's like a complete dead end. Turns out that in this long thread, you can do a whole bunch of stuff. Anyway, I figured it out. And in the spirit of open source, I did manage to get a PR merged on their documentation just to explain how you can do this. And essentially, the way that you do this is more complicated flowcharts and your sort of your very limited RAMs running out. You basically store a bunch of publishing flags. So you store a bunch of flags, which has the temperature change. And long story short, you have to go from a deep sleep to a quick deep sleep with RF enabled, and then it goes through the whole process again. So it does get a little bit more complicated. I'm sure my code could do with refactoring, but now you've got to store a lot more information. I mean, it's still not a huge amount of memory, but you have to make sure everything's 4-byte aligned because of the chip design. So it gets a little bit more complex, but it's still only a couple hundred lines of code to do all of this with, of course, lots of libraries behind the scenes. So how long does it last? About 88 days, and it's still running. So I've got 2 of these devices. One's lithium-ion powered, one's a AA battery powered, and I'm very happy to say they're both running. I've just looked at the clock. I've only got 5 minutes. This is where all the exciting stuff happens. Right, so from a data perspective, which is obviously what this is all about, you can store the data in Home Assistant with on InfluxDB. It's a time series database. You can bring that into a notebook. Influx uses SQL query. Bring in the data. Here you're looking at 3 sensors. The interpolation's terrible in matplotlib. But you can also do some cool stuff, like you can look at how many readings are you given a day, which is essentially the rate of change of temperature. So actually where I'm standing now, it seems to fluctuate a lot. You can read into that what you like. You can work out averages. And you can look at distributions of the time, how long things go to sleep before they're published. So on the whole, between 0 and 60 minutes is how long it will sleep for before it detects a significant change. You can also look, actually, if you combine this data with when the heating goes on, so that's the blue binary line, you can really see the effectiveness of your heating system. So this is how you can visualize the effectiveness of that. I'll skip through some of this stuff. Another thing you can do, which I'm doing right now, is I'm measuring the battery voltage And as you can see, I'm in a sort of linear regime. For 2 AA batteries, that should be 3 nominal. It's actually 3.45. So when you extrapolate, very basically, I should get about 11 months off this thing, which is brilliant. I was aiming for 6 months, but in theory, 11 months. So that's still going on. My next problem I had to solve, which I'm going to speed up now, was hot water cylinders. I don't know, this is the kind of thing you do in lockdown because you're in lockdown, but oil-fired hot water cylinders typically have electric thermostat overrides for boosting. Those controlled with bimetallic strips. You can't use these sensors, they're too big. You can find a smaller sensor. This is a Dallas 18B20 sensor. It's actually that small comparatively. You can solder that together, thread it through one of the thermostats, chop off the end, glue gun it together. You can then attach separate sensors onto the pipes themselves and wrap it. Not very effective, as we'll see, because you're trying to measure the internal water temperature through an external copper bond, and it really isn't a very good bond. So back to analysis we go. This is where we get a bit more data. I'm going to finish in 2.5 minutes. So here you're looking at, I've got the inlet and outlet from the oil boiler. I've then got the hot water is measured at the top, and I've got the hot water tube, which is the internal temperature. And basically the name of the game is to try and calibrate the difference between the temperature in the tube, which is more accurate than the temperature on top. At the moment, it looks bimodal. I've no idea why. If you calculate the diff, the boiler was serviced halfway through this chart, which is why you see a jump, but there's a 20-degree-ish difference. I might do some time series forecasting, probably not worth the effort, I'll take the average, but essentially that's one of the things you can do. And again, here you can sort of see the impact of switching on the electric immersion and the thermostatic effect as well. So basically this is now on a thermostat through that process. So to end, next steps, you can measure the current really anally if you want to further optimize. Really fun stuff. You can then, once you've got your sensor design down, you can create your own circuit layout and your own printed circuit board layout. And then, just to give you a sense, this is the cool snazzy bit. This is that module that you saw, the tiny thing, just for scale. This is a AA battery holder. So these things are really small. Basically, once I've chosen the right sensors, I'll mass manufacture these. If anyone wants one, you can ping me. I found another really tiny temperature sensor. It's 3 millimeters across. It's absolutely minuscule, so I'll probably use that in the future design. But really, Wi-Fi is not designed for low battery, so you can use UHF. These are digital UHF chips. And the reason why this is exciting, this is where I get my physics degree payoff, is because when you look at the transmission rate, the power that you receive is proportional to the wavelength. And as hopefully most of you will remember, the wavelength is inversely proportional to the frequency. So long story short, the higher the frequency, the lower the range. So by going low frequency, you increase the range. So that's something that I'm going to try with some outdoor sensors. This is what it looks like. This is one of the chips. This is a quarter wavelength antenna. The next thing is like crazy antenna design. This is a monopole, there are dipoles. This is a whole new world of exploration, which will keep me busy for another 3 months. My ending slide is really, if you're interested in this stuff, there's no better way than finding a problem to solve, like your home heating system, because that will keep you through all the issues. Credits where credit's due. I was inspired to do this through about 10 years ago by this guy called Nathan. He built a whole bunch of small sensors. This is now out of date because they don't make the chips anymore. Open Energy Monitor is fantastic. They provide whole bunches of, you can just buy this stuff as well. You don't have to make it. I just like making stuff. But the cool thing is a current transformer to make your not smart meter into smart meter. And my very good friend, Andy Bennett, who helped me with all the C stuff and embedded devices. So I'm going to stop there. Thank you very much, and very happy to take any questions.
Oh, great stuff. Yeah, if you have any questions, please put them in the Q&A. There were a couple of questions for Fetch AI that came late. I'm sure Fetch AI, you can write to them and they will reply. Is there any questions? I had a bit of a questions. Have you gotten into any type of kind of like control theory to get your kind of process of turning on and off the heaters, a bit more optimal?
Yeah, it's like the whole PID control thing. I mean, to
Yes.
be honest, the stuff that I'm doing is so simple. It really is just trusting the thermostatic control that they've built within the system. So
Yeah.
you set a target. I haven't really mucked around with it beyond that because it's built in. But you could, I mean, literally anything's possible. You've got the raw data. You can control the outputs. It's really around what the problem is you're trying to solve. So give me a hot room. Do advanced controlling for that. It's more the placement of the sensor that makes the biggest difference.
There's another question. Did you investigate Zigbee as a low power alternative to Wi-Fi?
Yes, so Zigbee, yeah, Zigbee's, it's on my list. Initially, I didn't go with it because it's sort of encrypted by nature, and I thought that would be a tax on battery. Essentially, Zigbee's going to be my post DIY UHF job. It definitely is probably a more friendly version of doing this. So yeah, it's kind of among the world of low energy stuff. There's also something called LORAN or LORAN. I can't remember, LORAN. That's another technology which is designed specifically for this kind of application.
There's another question. Have you thought about including external temperature?
Yes, actually. Let me just go back to a share quickly. I know it's sort of dinner time. One of the things that I've done, and I'll just show you, this is a bit more behind the hood. You see into my life. The central heating actually is only triggered when tomorrow's forecast, as the external weather service gives us, is less than 10 degrees. So you can do some fun stuff. So the night before, it checks tomorrow's weather, and based on that, it will switch on the heating. And super nerdy, it drops me a text via Twilio, so I know it's going to come on.
Cool. I think that's it. Any last questions before we finish? Frank, who asked that question, says awesome. So cool. All right, I think that's it. Well, thank you, everybody. Thank you, Amadeus, Joshua, and Aris. And then we'll see you in a month for our next meetup.
Thank you very much.
Thanks very much.
Everybody.
Thanks a lot.